Welcome to the preview video for Class 8 of Math S-322, and we're finally into calculus. Today we'll be discussing derivatives and one of the nicest theorems of differential calculus, the mean value theorem. So we finally get to apply all that you've been learning about real analysis to the subject matter that your students probably think is the most exciting in your advanced placement calculus course. Let's start with the definition, which ought to be familiar. We say that function f is differentiable at point A if, when we take the difference quotient, f of x minus f of a divided by x minus a, and form its limit as x approaches a. This limit exists and is finite, and we call it f prime of a, derivative. In this course, we will never use the dy by dx formulation of the derivative. That's a most unsatisfactory notation because it doesn't provide a good way of specifying where you are evaluating the derivative. Whereas here, when we say f prime of a, it's unambiguous that derivative is being evaluated at the point a. If a function is differentiable at a point, it's continuous there also. The proof is very easy, but the result is surprisingly useful, and we'll want to have a quick look at the proof. Theorems that we proved first for sequences and then for limits of functions turn into useful theorems for differentiable functions. And these are ones that are well known to anyone who has taken calculus. Suppose you've got two functions, f and g. They're both differentiable at some point a. Then the following are all true. Multiply the function by c, you multiply its derivative by the same constant c. Take the sum of two functions, the derivative of that sum is equal to the sum of the derivatives. Take the product of two functions. The derivative of the product, fg, is f times g prime plus f prime times g. This one's getting a little bit interesting to prove. And finally, the quotient rule. The derivative of the quotient, f over g, is g times f prime minus f times g prime in the numerator divided by g squared in the denominator. I hate to admit the way I remember this one is I remember the derivative of high over ho, which is ho d high minus high d ho over ho ho. And of course, this only makes sense if g of a is different from 0, so we're not dividing by 0. We'll be able to prove all these key results for derivatives quite straightforwardly. The best of all the differentiation rules is the so-called chain rule, which allows us to differentiate composite functions like the sine of x squared. What this theorem says is that if f is differentiable at a, and g is differentiable not at a but of f of a, then the composition g composed with f, which gives g of f of x, is also differentiable at a, and the derivative of g composed with f at a is g prime evaluated at f of a multiplied by f prime evaluated at a. This formulation is much better than dy by dx equals dy by du multiplied by du by dx. Students look at that and they say, that's obvious, you cancel the du's out. No, the proof is not that simple, and the statement is not that simple because it's very important that we're evaluating the derivative g prime at f of a while we're evaluating the derivative f prime at a. Our notation makes that clear. When we prove this, I'm going to restrict this to a special case. The special case is simply that there is some interval around the point A at which the function has a different value from its value there. Turns out that without that simplifying assumption, the proof is a real pain. I'll hint at how it gets done and show you a counterexample, but we'll restrict our proof to the simple case. A key part of most calculus courses is proving differentiation formulas. And you'll recall that with limits of sequences, we could either do these formal proofs involving epsilons and finding a big N that does the job, or we could use limit rules for limits of sequences. Same thing was true for limits of functions, and the same thing is true for derivatives also. It's kind of fun to go back to first principles. Here's an example. Suppose we want the derivative of the square root function. Well, we have to take the limit of x to the 1/2 minus a to the 1/2 over x minus a. You do that by multiplying numerator and denominator by the sum of these square roots, which is going to give us in the numerator x minus a. We've already got an x minus a in the denominator. We've got an x to the 1/2 plus a to the 1/2 in the denominator. This cancels when x is different from a, and when we take the limit, we've got two terms in the denominator, both equal to a to the 1/2. So the derivative is 1/2 a to the minus 1/2. And we've proved the rule: when you differentiate a power, you multiply by the exponent, you drop the exponent by 1. Here's an alternative proof which is actually more concise. The square root function has the property that its square is the identity function. So f of x squared equals x. We differentiate both sides. Applying the chain rule on the left, we get 2 f of x, f prime of x. On the right, we differentiate the identity function f of x equals x to get 1. Solving this for f prime of x, we find that f prime of x is 1 over twice f of x, or the derivative is 1/2 x to the minus 1/2 in one line instead of two. If we want the derivative of the 3/2 function, we could go back and do it from scratch. It's kind of fun to do that, but it's simpler to say that's x times the square root function. The product rule says we get one term where we differentiate the x to get 1. We have a second term where we differentiate f of x to get f prime of x, whose value we already know. Add the two terms together, we get the derivative 3/2 x to the 1/2. Your students should learn both approaches to proving the basic differentiation formulas. Now let's look at some theorems about the behavior of functions as related to the derivative of that function. These are very useful when solving, for example, maximum and minimum problems. The key theorem for maximum and minimum is the following, and this has to be stated very carefully. Suppose the function f is defined on an open interval. In order to evaluate the derivative, we need to be able to sneak up on a from both sides, and therefore we can't talk about derivatives at the endpoints of a closed interval, so we always use an open interval in talking about derivatives. If the function is defined on that open interval, has its maximum or minimum at some x0 in the open interval, and is differentiable there, then the derivative has to be 0. You can't have a maximum or minimum where the function has a derivative that's different from 0. It's entirely possible to have a maximum or minimum at a point where the function fails to be differentiable. Next, Rolle's theorem. Most people know this as a special case of the mean value theorem, but it turns out that frequently, when you're trying to do proofs that look as though they require the mean value theorem, it's best to modify the problem so we're only using Rolle's theorem. Rolle's theorem says the function is continuous on some closed interval, it's differentiable on the open interval, and furthermore, it has the same value at both endpoints. What makes this different from the mean value theorem is this extra requirement that f of a equals f of b, and what Rolle's theorem says is there exists an x in the open interval where the derivative is equal to 0. This theorem requires something we already know, namely that on a closed interval, a continuous function actually achieves its maximum and minimum. That in turn had to be proved using the Bolzano-Weierstrass theorem. So proving Rolle's theorem in an introductory calculus course is a bit dicey. To do it right, you have to go back and state and prove Bolzano-Weierstrass. From Rolle's theorem, it's easy to get the generalization, the mean value theorem. Again, the requirement is continuous on the closed interval, differentiable on the open interval. And the mean value theorem then says there's an x in the interior of the interval where the derivative is equal to the change in the function value divided by the change in the argument. Wow, we're done. That was quick.